Due to technical difficulties, we are joining the program already in progress.
But we found graph visualizations to be optimal for answering these types of questions. So, in the next few cells, we group the logs by the attacker address and the destination address. In the next few cells, we group the logs by the attacker address and destination address, and then count the number of unique events between the two. We then treat each aggregated log as an edge and each IP address as a node, and then upload the data into our tool. So, in this visualization, again, each node represents an IP address. The light blue nodes are the target addresses, and the orange nodes are the attacker addresses. Immediately, our attention is brought to these three orange nodes, which form this flower-like pattern. We can investigate some of the alerts coming from these IP addresses, and we see that most are named session closed, with the name either TCP fin or TCP reset. At this point, we can start to hypothesize that what we're witnessing is some port scanning activity. These IP addresses are basically going and knocking on a bunch of doors on a bunch of different IP addresses to try to see if there are any services that are running that they may be able to exploit. So directly within the tool, we can filter out some of this port scanning noise in order to determine if there were any other alerts coming from these IP addresses. So sure enough, we see that there were in fact some non-port scanning alerts coming from these IP addresses. If we hover over some of these edges, we actually see that in particular there were many successful logins coming from these IP addresses. Now, taking a step back, this is pretty cool. We successfully went from about 1 million high priority events to about 4 to 5 different clusters of attack patterns that we can kind of handle in conjunction. We have our port scanners down here, and then 2 or 3 other kind of alert patterns that can now be handled. So, hopefully this gives you an idea of how graph analytics can be used to help with scale. The second pain point we discussed is heterogeneity. Many of you know firsthand there's been an explosion in the number of security products needed for protection, and it's becoming increasingly difficult to investigate across them all. The consequence was described to us as swivel chair analytics, a term describing how analysts must swivel between many different security products they might use. In addition, another common consequence is described by the streetlight effect. And this term is taken from an old joke about a drunk who lost his keys under a streetlight. When a police officer asks the drunk if he's sure he's lost his keys here, the drunk replies, "No, he lost them in the park, but there aren't any lights on there." I didn't say it was a good joke. All right. This seems relevant because oftentimes we've heard analysts are collecting logs from many different products, but they tend to only look at logs from 1 or 2, because extending the investigation to other tools is simply too difficult. So the question now becomes, how do we put more of these tools in reach? So, we believe that by using graphs, we can more easily look across various security products. So long as we can extract various entities from these logs, such as endpoints, servers, URLs, IP addresses, we can start to visualize the alerts as edges connecting the various entities. Here at Graphstry, we refer to this type of representation as an alert graph. By focusing on the entities an analyst cares about, we can easily pivot to expand and narrow the investigation across many different tools. So I'm going to show you another demo where hopefully this will kind of show you the value of this alert graph. So here we're showing an alert graph of one single FireEye alert. And we can extract 4 different entities. In the center, we have an IP address colored blue. We have an alert name colored red at the bottom of the screen indicating this alert was named a malware callback. The file hash of the malware is colored pink at the top. And finally, we have the malware URL colored yellow. A logical first step of analysis is to search FireEye for any other alerts that may have similar entities. So we can do this and again represent it as an alert graph. And what we see is that there was in fact one more alert that had the same file hash and the same alert name, but it was actually calling back to a different URL. So at the bottom right of the screen, we see the URL 198644b12e.com, and at the top left of the screen, we see 25643e662a2.com. We can assume at this point that the malware is using some sort of domain generating algorithm, and we can't rely on these URLs since they're likely exchanged and generated rather quickly. So to be clear, in a simpler scenario, we may be able to just search through the logs and see if there were any connections to these URLs. But since we suspect a DGA, it becomes necessary to find what external IPs were hosting these URLs by joining the proxy logs. So now we're going to join the proxy logs, and we're going to connect each external IP address to the URL they were hosting. It's now pretty clear that although these two malware instances were connecting to two separate domains, they were hosted by the same network of IPs. And this is a perfect example of where graph visualization thrives over traditional visualization techniques, because we really care about the connections. Here we're dealing with probably only 50 or so logs, but it'd taken analysts some time before realizing, oh, they're actually connecting to the same network. So at this point, the analyst might ask, why would a URL be hosted by 20 to 30 different IPs? What we believe we're visualizing here is a fast flux technique, which is a DNS technique used by phishing and malware delivery sites, which basically hides them behind an ever-changing network of compromised hosts acting as proxies. So hopefully this should already show you the value of graph visualization. But our goal is to allow analysts to keep digging deeper. So now that we've exposed the malicious external IPs, let's join in our firewall events to see if we can find any more connections that FireEye may have missed to our suspected botnet network. So now we're going to join our firewall logs, and sure enough, what we're going to see is that there actually were a large number of IP addresses that had connections to our suspected botnet network. To dig even deeper, we can now add in our intrusion detection and intrusion prevention alerts to see if there was any suspicious network activity going on with these internal IP addresses. So, first, let's look at the two red nodes at the right of the screen. These show that most of these IPs generated past traffic alerts, but also that the traffic was associated with an adware toolbar, which may want to be looked into, but this is usually benign. We can hypothesize that most of these connections aren't truly malicious, but that we had a few machines download some adware toolbar. At the bottom of the screen, we noticed that we had 3 IDS alerts mentioning a suspicious file download and peer-to-peer traffic. The peer-to-peer traffic is particularly worrisome because botnets often use peer-to-peer traffic as a means of communicating with other bots. Now these IP addresses need to be investigated further. To do so, we can join in DHCP logs in order to trace the suspicious network activity to a particular device. And then we're going to filter around the time of these suspicious network events in order to see what device was assigned this IP address around that time. So now we've successfully taken these network events and we have an actual endpoint which we've correlated generating these network events. And if we wanted, we can take this even one step further and connect this device to the user activity using endpoint protection logs in order to find any suspicious user activity going on this endpoint. And just to show you another kind of useful feature of our tool, now I'm going to encode these endpoint protection logs by the alert name. And so what we see here is each orange edge represents a failed login. The green edges represent a successful login. And if we hover over the final edge, what we see is that this actually indicates that the audit log was cleared. So given the whole rest of the context of the graph, this is pretty suspicious. So hopefully this demonstration showed how graph analytics can be used to easily track suspicious activity across various security products. Okay, the final pain point we're going to discuss is training, specialization, and collaboration. So as I kind of just talked about, these alert graphs can kind of provide a common representation across many different tools, and then these can be used as kind of the common representation across many different analysts who may have different skills. So we're still prototyping this, obviously, as you can see by this rough mock-up, but I wanted to quickly describe kind of the product we're moving towards. So the goal is to create a product that encapsulates all the steps of the investigation into one clear view. And so this picture right here is supposed to represent the demo I just gave. But now you shouldn't need a narrator to describe the entire investigation because each step of the investigation is described in the table below. This allows analysts to very easily collaborate with other analysts of different areas of expertise. So you may have your expert network analyst investigate the IP addresses and your memory forensic guru check out the endpoints. Then you can publish this investigation as a template, so when another FireEye alert comes in, you can basically re-execute the workbook to perform all the same steps of investigation, even if your memory forensic guru may be out of the office that day. And when the investigation is complete, the workbook should contain all the relevant data and can be used as a report of the incident. So, summary of the demos. We're currently dealing with too many events, and we need a way to scale visualizations without just summarizing the data, and graphs are really good at this. It's difficult to piece together different and diverse events, and so this concept of the alert graph can help unify views, analysis, and workflows. And lastly, collaboration, sharing, and hands-off is difficult, but these alert graphs can kind of provide a common language between analysts of different areas of expertise. To give you an idea about where we fit into your toolbox, we're not a compute engine or a system of records. We realize most people are already paying a substantial amount for their Splunk or ArcSight installation. Our goal is to provide a greater return on investment on the products you're already using by providing insightful views of your data and a platform to share your workflows. A couple notes about our technology. We're actually utilizing GPUs on both the client and the server. I really love this stuff, so if you're interested as well, I'd be happy to talk to you more about it, but it's a security conference, so I'll briefly move past this. All right, that's the end of my talk. Thank you very much for listening. Special thanks to Jeff. You've been a great mentor. I appreciate it. We're currently looking to hire a security researcher, data backend engineer, and UI and UX developer, so if you're interested in those roles and thought this talk was interesting, please don't hesitate to reach out. With that said, do I have any questions? Sure.
Wait, 1 second.
I was just wondering, what are you using for the back end to do the classification in terms of like that's malware? How are you identifying certain events or items as that versus something else?
Right. So right now we don't do any classification. We really do hook into your SIM. So kind of whatever your SIM is currently doing, we can kind of load that data and create a graph from it. So in that example, we were looking at ArcSight. And so we saw that there was a malware, and we basically just parsed that information into an alert graph.
Since log formats can be different, what do you do for pulling in data from different devices, or do you have to pull it in only from the SIM, which is already processed in all the different formats?
Right. So I mean, there is going to be some work for each product. We're going to need to figure out, okay, where are the IP addresses held? Where are basically all the entities that you care about? We're going to need to go through and parse that information. But hopefully, once we do that, we can kind of most alerts are going to have an IP address, or most alerts are going to have a port number. And so by doing that, we can still hopefully look across the different log types. But yeah, there is going to be some manual work there if it's not in a SIM.
So, thank you. What are the current SIMs that you're able to integrate with? It sounds like you mentioned Splunk. Do you have like logarithm? Can you give us a list?
What was that last part?
The current SIMs that you're able to integrate with.
Right. So right now we're building our Splunk adapter. So you can use the notebooks to basically do very ad hoc integration. So I kind of showed you one example of looking at ArcSight logs. The first adapter we're building is Splunk. So we really want to be doing a lot of things within Tool. So we're kind of the first adapter we're building is for Splunk. That has been on our radar, but it's not set in stone yet. But at some point, we are going to need to deal with products that don't have a query engine or any sort of API to pull data, in which case we'll probably have to put it into kind of our own back end and figure out how to query it. All right. Thank you very much for listening, guys.